Okay guys, so today's stream is going to be, let's turn down the volume first on everything, make sure that's all good. Let me get this all set up, make sure this is all good. Yep, seems to be okay so far. No lost frames or anything. Okay. So today's stream, as you can tell from the title of the video, is 3D cameras. So what we're going to be doing is going over how to make a quick first-person shooter camera. I'm also going to be talking about some other stuff that I'll get to later, but it's going to be some brief stuff. But this is what the final results are going to be. You're basically going to have this camera that you'll be able to move around in 3D. We're not going to handle rotations today. It's just going to be kind of keeping it simple of a very simple first-person shooter camera. Rotations, however, will work, of course. It's pretty straightforward to get it working, and I'll leave that for an extra assignment. But for today's stuff, we are just going to work on that. So let me see if this will work. If not, we'll go over it in a future video. So yeah, that kind of works, but I don't really want to go into it today's stuff. So we'll go over that later. For today's stuff, we're just focusing on translations. So what does that mean? Well, let's start with the basics. So first off, to begin, remember that last time what we did was we just got our basic model rendering. We also have our state machine, so you can translate back and forth between states. So this is state 1, this is state 2. We have a 3D shape being rendered using OpenGL. We kind of went over shaders and some of the basic applications of them. So we have our vertex shader and we have, our fragment shader. So today's extension of that is going to be passing more data into those shaders to be able to go through and manipulate things and move them around, such as in that other application. Now, I didn't stream that this week. I was really busy with some stuff. Today's my birthday, so I've got a lot going on for that. So that's why I am going to be keeping this very brief and why we're not going to be going over rotations. I just want to keep this short, sweet, to the point. Rotations will be a pretty quick thing to cover next time. But this is a kind of a good start to moving around cameras and objects within your game in a pretty quick and easy way. So what we're going to be doing is we're going to be creating a camera class, and we're going to be adding some more onto our test state and more onto our shaders, because there's some other things we're going to need. So I'm going to close a lot of this to start with. We don't need our fragment shader today. Test state.h we'll come back to. Drawable shader we need to keep up. Okay, so now that we have this, what we are going to do is we are going to start out by talking about, first off, what exactly we're going to be passing to the shader, and then we're also going to talk about what is needed as far as mathematically to do this. There is some pretty tricky math. It's stuff that I'm not the best with, but I've gotten the hang of it enough now to where I can do some neat stuff with it. We're also going to be using a fantastic little library called glM, which is going to kind of help us to go through and be able to do all this crazy math without having to worry about, going through and writing all the calculations ourselves. So this is the library. It's called glM. It's OpenGL Mathematics. It comes with a lot of stuff that's just really nice and easy to pass through to our shaders, and that link will be in the description on the YouTube video if you're watching this afterwards on YouTube. So to kind of start things off, let's go ahead and talk about uniforms. So we had I think I briefly glossed over this last time, in that there are a couple of different types of ways you can pass data through. One of them is you pass through the data each and every time, which in this case is in the form of positions and colors. So each vertice that is processed could have a different value for these. However, there are certain values that are going to be the same for each vertice. So for example, each vertice that makes up, in this case, our quad, which is these four corners, is going to have different properties. But there's going to be certain things for the overall shape that remain the same. In this case, the position of the shape is at 0, 0, 0. Okay, so that's at the very center of the 3D space. And so that's going to be the same for all 4 of these. Same thing with its rotation. The rotation of this model is going to be the same for each vertice. The vertices' individual positions might change, but the overall position of that shape stays the same. So really, for each vertice, we don't want to be changing certain values each time. There's going to be certain values that stay the same. And so the position and the rotation of this will stay the same throughout. So what we will be doing is we will be using what are called uniforms. Uniforms basically meaning that they are uniform throughout the entire model. So, okay, so what kind of uniforms are we passing? Well, at first glance, it might seem to make sense to pass in the individual components. So we might think to pass in individually the rotation of this model, the translation of this model, and then the scaling of it. But really, all 3 of those are going to be the same. They're eventually going to be combined in the shader, so really we actually only need to keep one set of values for that. And so really, it's actually just going to be one uniform value model matrix. So a matrix is, in this case, why can't I save you? Oh, because it's being used. So the model matrix will look something like this. We'll go ahead and 1, 2, 3, 4, and then so this is kind of what a matrix would look like. And I'm gonna kind of explain parts of it to begin with, but this is a little bit more complex than I'd really like to get into right now. So let me go ahead and find, I had a good document that kind of explained this. Here we are. So this is a pretty good website. This will be in the description below as well. So this will be in the description below as well for this website, which is a basic overview of some of the matrices and things of that nature. Oh, am I offline? Nope, it doesn't look like it. Okay. Just making sure. I'm paranoid about this today a little bit because I know that we've had so many issues in the past. So to kind of go through, there's some basic stuff on how these matrices work and such and how they're set up. But the basic summary of it is that the X, Y, Z positions are actually going to be, and I'll post this below, but they are actually going to be right here. So this is X, this is Y, this is Z. So this is where your actual X, Y, Z positions are stored in here. From there, you have the scale of X, the scale of Y, the scale of Z, and you'll notice that there's this 4th property here. This is called W. This is generally kept at 1. It's basically made to be able to easily multiply, divide, and translate these matrices around without a whole lot of headache. So that's why that is there. Let me go ahead. I'm going to move this over here so I can see this a little bit better. Keep an eye out for drop frames and such there. And I don't know, something seems to be going on with Twitch chat where I can't actually see anything. Maybe it is working and my video is just not loading. That could be it as well. But hopefully if you guys have questions, post in the chat. Hopefully that'll work. Let me go ahead. My internet has not been very good these past few days, so I'm hoping that everything is working okay. Alright, continuing on. So this is kind of our scale X, our scale Y, our scale Z, our X position, our Y position, our Z position. Now you might notice there's no rotation there. Rotation is a pretty complex one. That's one of the reasons why we're using this library, and it's another reason why I am not going to go into it. But the basic summary is that it looks something like this, where basically if we want to rotate a point, we have this weird matrix stuff, and then we have the matrix combinations for everything. And so the rotation matrices look really, really weird. They're not something we can easily draw here, and I'm not even going to try to do so. But long story short, a matrix can basically store our 3 properties of translation, rotation, and scale. So we only need this one because it stays the same throughout. As a result, we don't need to do anything else. So I need to give 1 second. I will be right back. maybe came on downstairs. So we have our model matrix. Now this is only good, however, for displaying that one model. Oh, why is Twitch not loading for me? This is really quite annoying. Okay, there we go. Okay, so we have our model matrix. Now that everything's settled, model matrix is going to basically control the rotation, scale, and positioning of that model. However, we also need to do the same thing for the camera, and the reason is that we basically will be taking the entire world and moving it around the camera. The reason for this, if you think about it, with a normal real-world situation, we might have you know, our object that we're trying to view, and we have our camera, and we move the camera around the world in order to get different viewpoints. However, with 3D games, that's not quite how this works. The basic way that we do this is we actually move the world around the camera. So when we move the camera to the left, okay, so if we have our camera, we move it to the left, we're actually translating the world to the right. And this might sound weird, but this is how things are done. And so really what's going to happen is we're going to have a world view that is going to be the inverse of whatever we're moving the camera, the opposite of it effectively. So if we're moving one to the right, then this will hold one to the left as a result. So we're actually going to have another uniform. Oh, and this should be MAT4. So now we're also going to have uniform MAT4 view matrix, which is the view of the world currently. And so that's what that is. Finally, however, so we have our camera, we have it adjusted. Let me get these again. We have our camera, we have where it's viewing, but the big thing is that we now need to actually identify each viewpoint, each pixel effectively on that view into the camera space, okay? The way to think about it is that the camera can only see in 2 dimensions. It can't actually show in 3D. So we have to tell the camera how to map out each point onto there. And so there's a specific type of matrix for this. It's generated by this library as well. It's called a projection matrix. And so we're actually going to also need that on here as well. So we have these 3 matrices, and what's going to end up happening is pretty simple. It's just going to be project matrix times the view matrix times the model matrix times our position. And so each vertice will be updated with that. Now, really in this case, we actually don't need the model matrix because our current test shape is not going to actually have its own position. We're not going to be worrying about that. So we can actually get rid of that because it's just going to be at the origin of 0, 0. Now, as a result, we can get rid of that. Now, the big thing to realize is that, again, remember how I said that the X, Y, Z positions are going to stay the same for the model, and the rotation is going to stay the same, and the scaling is going to stay the same throughout all of the vertices? Well, the same thing actually goes for the projection and view matrix. Once you move the camera, then you render everything. And so really, these 2 matrices are actually going to stay the same as well. So we actually don't need 2 matrices, and we don't need to do that. We actually just need one, which is the MVP matrix, the model view projection matrix. And the reason being is that you don't want to, right now we're going to be doing 3 operations every time the vertex shader runs. We're going to be multiplying 3 matrices every single time. And that's, you know, it's not terribly expensive, but it does add up over time, especially if you have thousands and thousands and thousands of vertices with these large models. You know, when you're loading your 3D models, that's a lot of calculations. So what we can do to kind of simplify this is just have one MVP matrix. We calculate this once on the CPU and then just pass it into the GPU each time. And so each vertice would then be set up with this position. Now you might be wondering, you know, each of our vertices here, we're actually bringing them in. Why not do the same thing on the CPU side there and just pass in one final value? Well, the reason is that when we pass between the CPU and the GPU, there's a cost. That's expensive to do operation-wise. And so if we update all of the vertices on the CPU side, we have to pass all of those new values to the GPU side. And so every single frame we would be passing those values between the two. And so that's a very, very costly. It's much, much more costly. And as a result, we would actually be losing speed because every time the position changes, we'd have to repass them in. Whereas right now, if we just keep it with this way, we pass them in once, and then we only update the MVP matrix going through, which is a much, much cheaper cost. So that's why we're not going to do anything crazy like that. So we have this model view projection matrix. So now we need to actually go ahead and be able to pass this value into our shader. So we're going to need two new methods. The first method right here is going to be glint get uniform. Let me just make sure I didn't name it weird. I want to make sure it's consistent with what I have over here. So we have get uniform. Okay, cool. So this is going to be get uniform location. If you remember with our get attribute up here, we have to get the actual location of that uniform value in order to be able to do anything with it. So we have that. We also are going to, however, add a void, and this is going to be in this case. Move that to the side a little bit so I can read it better, which is going to be set uniform matrix, which is going to again take in a glint location, and then it is going to take in a matrix, which we need to get this library for. So rather than creating our own matrix class, what we're going to do is we're going to go ahead and we're going to use this OpenGL mathematics library. Now, I've already gone ahead and downloaded that. As soon as you go ahead and you download that, you will be able to see this directory here, which has all of these different files. And really the only directory we need here is this GLM folder. The reason being that the GLM is going to, is this the one? Yes, this is the one. The GLM folder, so this library is very nice in that it's only headers. You don't actually need all of the additional, you don't need to compile anything, you don't need anything extra. We just need the header files that come with it. And you'll notice that everything in here is just header files. It just makes everything a lot easier. There is some C++, but we don't need to worry about that. And so including this is pretty straightforward in that all we have to do is come up to here. Let me make sure I'm not getting... Okay. So now we're going to come up here, do include, and this is going to be glm/glm HTTP, which includes what we need, and now we have our matrix includes right here. So now that we've got these two methods ready to go, what we're going to do is we're going to go over to, let me get this file open on here again. Some questions going on. Okay. So now that we have this going on, we're going to need to go over to our shader, and we're going to have a few different things going on. So I'm going to go ahead and I'm going to minimize these a little bit, just to give us some more breathing room. And we're going to have a few new methods now, of course, which are glint get shader, get uniform location, which takes in a string name. And all this method is going to do is it's going to actually be very, very similar to our previous version, except instead of returning, so if we come up here to the get attribute, normally we're doing a get attribute location. It's going to be get uniform location, this shader program, and then name C string. Because again, remember, OpenGL is really designed for C, so we need to make sure that's a C compatible string as a result. What is... Okay, so now that we have our uniform location, and this is going to be where it differs a little bit. Last time we got this attribute and we did not, we held on to it elsewhere. We did not have a way to set it from in here. This time around we're actually going to do that because it's going to make our lives a little bit easier, and you'll see why. We're going to have this set uniform matrix, which is very specifically for setting a matrix uniform value. You can, of course, have other types of values. So you can have, vectors, you can have just integer values and such, but those are not what we're worried about. We're just worried about matrices for the time being. So we're going to have this, and all this is going to do is it's going to call glUniform matrix for v, fv. And real quick, I'm just going to fill it in. It's going to be location 1 gl false. And then we need to actually, so this method expects a pointer, so we need to use the method value ptr matrix. And if you notice, even though we included that GLM header here, it doesn't actually work. And the reason being that we actually need to include one more library, which is going to be this one right here, glm/gtc/type pointer. This is basically this basically includes the method that we need to convert this pointer to a pointer, because again, this is expecting a pointer. So let's go ahead and we'll bring up the description for this method, which if you go ahead and you search for it, you're only going to find a link to glUniform. Now the reason for this is that glUniform takes in a variety of types. Remember how I said that it can be a matrix, it can be a float, it can be a vector. This allows you to account for each of those. So you'll notice right here, glUniform 1f. That stands for glUniform 1 float. So we're only passing in one float value here. As you can guess, 2f allows you to pass in two floats, 3, 3, 4, 4, so on and so forth. 4i, or the I instead of an f, is for integers rather than floats. Now, of course, it's not always convenient to pass in just 2 or 3, just 3 values like that. So we can actually use pointers to a list of floats. So we can basically store an array and then pass that in instead. And in this case, what we're actually doing is we're passing in matrices. So if you look here, there's a version for matrices. Matrices, again, are formatted in that way that I drew before. And so you can have a 2x2 matrix, a 3x3 matrix, or like we're using, a 4x4 matrix. And so this takes in the location of the uniform, it takes in how many matrices you're passing in, and then it takes in a transpose value. So basically, you can transpose a matrix. This is useful if you're doing matrices using, left-hand notation, and then I think OpenGL requires right-hand notation, right-hand significance. I forget the proper terminology, but in this case, because we're using GLM, we don't have to worry about that, and so as a result, we don't actually need to worry about this. It's just going to be false, and then we pass in our pointer to our value, hence that need for the GLM value pointer that we use right here with our matrix. And that's why we're actually making this a method, is that we only want to pass in the location and the matrix. We don't want all this extra values and all these extra things we have to do being passed in. So once we've gone ahead and done that, we've gone ahead and finished this off, and we are basically all set at this point. The final thing, which I forgot to do, is make sure that we call that from there. And now that that's all done, our shader method is now up to date. So now that we can pass values into our shaders, we need to go through and actually create a way to utilize this. So we could go ahead and have all the different matrices stored throughout, but it's actually going to obviously be a lot easier to make a camera class. So let's go ahead, we'll do new item. Oops. We'll come to headers, and we're going to make a class called camera. So camera, to kind of kick things off, is just going to be camera as the name. We're going to have some public stuff, and we're going to have some private stuff. So on the private side, we need to store a few different things. We need to, first off, we need to go up here, and we need to make sure we include the glm/glm-hpp. And HPP is a C++ header file. This library is very specifically for C++, so that's something to keep in mind. Though, of course, this is going over tutorials in C++, so really that shouldn't be an issue. So now that we have that included, there's a few different things we need to include. First off, we need to include 2 matrices. We need to include our projection matrix, and we need to include our view matrix. Next, we also need to store a matrix for our translation, and we need to store a matrix for our rotation. And the reason for this is that GLM has some great functions to go ahead and handle all of this for us. It'll make our lives easier in the long run. Next, we need to store a pointer to our shader. The reason being is that the camera is going to pass in all those values and update it on its own. All we're going to do is if we change scenes, we might keep the camera around and just change the pointer to the camera, or the pointer to the shader instead. Next, we need our view projection uniform value, which stores the location of the view projection uniform. And as to why this is highlighted red, we're going to go over that in a little bit. The reason being we're not having some includes, we're going to include them a little bit differently. Finally, we're going to have one more method, which is update world matrix. So you'll remember right now that we have our projection matrix, we have our view matrix. View matrix is the view of the camera. What we actually want to do is we want to combine the translation and rotation every time they're changed into the view matrix. So rather than updating that in an update loop, we're going to have a method, update world matrix, which combines these two. And actually what we'll change this to make it more clear is update view matrix. An update view matrix is basically just going to update this view matrix with the combined values of these two. And that's going to be pretty simple. We'll go over that in just a second. But for now, let's go ahead and add a couple more methods. The first is a camera method that takes in a pointer to our shader that we want to give it. Then we're going to have a set shader method, which takes in a shader pointer and will let us update the shader. Next, we're going to have a couple of methods for changing the translation and rotation. First off, we're going to have a set translation, which takes in an X, a Y, and a Z method. And then we're going to have a float set rotation, which will take in a float rotation value, and then the X, Y, and Z axis along which to rotate this. Next, we're going to have a translate method, which also is going to translate, but it's going to do so a little bit differently, and we'll explain that soon. And we're going to have a rotate method that will take in another rotation, float X, float Y, and float Z. And again, these might seem similar, but they are going to be different, and I'll explain those soon. Finally, we're going to have an update method, which will update our shaders with all the proper values. So now that we've got those, let's go ahead and add our camera source code. So we're going to come here, we're going to take this and make our camera C++ file. Now the camera C++ file is going to include a few things. The first thing it's going to include is it's going to include windows.h and our gl/glu file, because we need those in order to use our shader. And that needs to be included, of course, before we include our camera, because again, we're using the shader class over here, and in order to do that, it has to be included here so that it can take effect under those. Now that we've done that, we're going to come down here and we're going to have camera, shader, and then we're going to set the pointer to our shader in here to that. So now that's stored, and then we're going to have our VP uniform be retrieved, which is going to be equal to this shader get uniform location, which is going to be, in this case, our, what do we call it? I think we call it MVP uniform. We will check that real quick to make sure, which in this case, MVP matrix. So that's going to go ahead and get a pointer to that location here. So once we have that, then we're going to need to go ahead and create our projection matrix. So what we're going to do is we're going to call GLM perspective. Now you'll notice that that doesn't actually show up immediately. The reason for that is there's two more headers we need to include. We need to include GTX/rotate vector, and we need to include as well GLM/GTX/transform.hpp. So now that we have those, if we come here, we have this perspective method. So those basically those methods are included separately. In order to do that, we need to include that extra stuff in order to be able to use that. So now that we have those extra methods, and there's some other methods that those also include, which is like translate, rotate, and some other stuff. So you can look up more of that online at GLM's documentation. I'm not going to go into that. The big thing we need is now we need to convert our field of view to radians. So we have to go ahead and make our field of view. I'm making it 45 in this case. That's obviously able to be changed. The other thing we need to do is we need the width, the aspect ratio, which is going to be the width divided by the height of the screen view. We need our near and our far. So I'm going to go over these in just a sec. So the first thing we want to do is we want to pass in on top of our shader width and height of our screen. And this is going to, of course, need to come into here. So we're going to take this, copy and paste that. So the width and the height of the screen is basically going to give us an aspect ratio for how big of a view the camera has. Basically, if you're taking up the entire screen, you want it to have the appropriate aspect ratio to not look all distorted. The value right here is the field of view. So you can set a bigger or smaller field of view. Sometimes this is adjustable in games. And we can add that later. Right now I'm just setting it to 45 because that's a pretty good standard value. But basically this is how much of the scene can be seen from a horizontal aspect. Finally, we have these two values. So we have the near value and the far value. So basically anything that's closer than 1.0f is going to basically not be visible. And anything further away than 1000.0f is going to not be visible as well. So basically there's a certain range where everything is visible. The idea being that we need to be able to map out in our perspective what's visible. And anything beyond that we don't really need to draw. It gets to the vanishing point. And so that's what those values are. So now that we have those, the next step is to go ahead and we need to set up our camera set shader method, which is just going to take in a shader as well. And in this case, we're just going to update the shader, and then we need to get the new uniform location. The reason for that being that the uniform location might change between shaders. So now that we've done that, we need to go ahead and do our set translation method, which takes in a float x, float y, float z. Now this is kind of the first part. You'll remember that I said that we need to go ahead and we need to have two of these methods. So set translation is basically going to set the position of the camera. So if our camera is at position 555 and we want to set it back to 000, we pass in 000 and that's what it sets it to. The new position will be 000. And so what we need to do is we need to do this translation is equal to glm translate glm mat4 1.0. This is what's called an identity matrix. This is basically a matrix whose origin is 000. It doesn't have any scaling or any rotation applied to it. It's just a zero. It's just an origin location effectively. Then we need to pass in a vec3 of our x, y, and z positioning. And then finally, we're going to have to call that update view matrix. And that is how we're going to translate our matrix. However, there's another way we could do it. So remember, if we're starting at position, and I'm going to put this in comments here, if we're starting at 555 and we call a rotate of 000, or translate, sorry, that's then going to equal 000 as our new position. However, there's another method we have that is called translate. So translate, what this will do is if we are starting at position 555 and we call translate 000, the new position is actually going to be 555. Basically, this translates from the current position, incrementing it by a certain amount. So if we call 200, then this is actually going to translate to 755. Okay? And this will get useful when you start moving your character around. When you push a key, you only want to increment it by so much. So we want a method to be able to do that as well, rather than just updating the position. And the change to this is actually very minimal. All we're doing is instead of passing in that origin, the identity matrix, we're going to pass in our translation matrix, which will then update that translation as such. Now, we're basically going to be doing the same thing. I'm going to go ahead actually and erase this these comments. We're going to be doing the exact same thing for our rotation, where we have a set rotation, which takes in float xyz, and rotation. And it's going to basically do the same thing, except it's going to call the rotate method. So rotate, if we go ahead and we do that, takes in one additional value, which is going to be GLM radians rotation. And this is basically going to say rotate by this many degrees by these values along the z-axis, which basically this is very, very similar to how quaternions work. This is not Euler angles. That's why I don't really want to go into rotation today as well. It's going to be a really whole separate subject of discussing Euler angles versus quaternions. This is kind of, again, there's a lot to begin with for OpenGL, and this is going to be an important thing as well. So now that we've gone ahead and done that with our identity matrix, we're going to do the same thing here. So we will have the ability to rotate the camera, but we're not going to be utilizing it yet, just because, again, I want to discuss that more before we really start going into that. So that'll be saved for next time. So now that we have rotation and translation, we're going to do the update method. And the update method, all that's going to do is it is going to take in our shader, and it's going to then set the uniform matrix of VP uniform to this project matrix times this view matrix. Now you'll notice view and projection our matrices are actually not normal float values or anything like that. They're matrix values. And this is because this is why I love GLM. It is just the best library for this. This overloads the multiplication and addition operators so that we can go ahead and we can do stuff like just multiplying two matrices by doing it like that, rather than calling like a GLM multiply or something weird like that. I believe they do have that. I can't remember off the top of my head, but I believe that exists, but this is an easier way to do that. So the combined value of these two will be passed into our shader. Finally, the final method we need is our update view matrix, which all this is going to do is take our view matrix and it's going to set it equal to the rotation times the translation. This is a very important order, by the way, because the order of these operations can completely change how this works. So what this is saying, okay, so let's say we have our object, okay? So let me make sure you guys can see this, okay? So we have our object, and we are telling it that we want to move it up and then rotate it, okay? So if we start out by moving up and then rotating, what this is actually going to do is it's going to rotate it based on the world rather than based on the, it's going to rotate it based on the origin rather than the world. So if we do this, and this is where things get tricky, it's going to rotate it like it were up here. And so what it's actually going to do is it's going to do a much smaller rotation and then move it up. That's not what we want. What we want to do is we want to move it to this position, then rotate it. The reason, and this is where things just get really, really complicated, because again, it's all backwards. It's really, really complex math. But effectively, we want to rotate it first, then move it up. We don't want to rotate it based on if it were up here, okay, if that makes sense. We want to rotate it as it is and then move it up. And so, and this is where things get so weird, because if we were rotating it like the point we're up here, it's going to rotate like this, and then when we move it up further, it's going to move up like this. And that's just not right. What we want to do is we want to move it up, then rotate it like that. So we actually have to rotate it as if it were down here, then move it up, and then we're done. Okay? This is a very, very important order. It is critical that you do it in that way. Now, that, of course, allows us to do some really cool tricks later on, especially when we get into our 3D modeling and animation stuff, because then you can start rotating entire arms based on that kind of concept, where if you rotate your arm, maybe this is an extension and it does stuff like that. But in this case, you want to rotate, then translate, okay? Now, the same thing goes for scaling. There's a specific order for that. a very, very specific order that we want to do that in. And again, that page that I linked to, this one right here, I believe it specifically says on here where the order is. If not, I'm going to be very, very sad. And it does not. So let me go find that other link for you guys to make sure you have it. And here it is. So this is from Stack Overflow. This is a good reference sheet to keep handy because I know it's very confusing. Remember, rotate then translate, but if you're adding and scaling, you want to scale, rotate, translate. The reason is you want to grow it out. Okay, you're stretching it, rotating, then translating. Okay, that's very important ordering. If you do it out of order, you can get some wacky results. And then if you want to rotate around a certain point, okay, so if you want to have an object that you're rotating around, okay, then you will add in the point of translation, then rotate, then the object's translation itself. This link will be below. Use it as a reference. I highly recommend having it around, but this is very important ordering to keep in mind for everything. Okay, guys? Alright, so now that we've gone over that, I hope I've emphasized the ordering of that and how just crazy important that is. Let's go ahead now and get started on the final phase of this. So the final part that we need to do now is we need to come over to our test state, and we're going to start updating that. So we have all the stuff to do this. We now need to go ahead and actually get it set up. So we need to start by including our camera in here. We're going to include camera, and we're going to just create another camera object here. And then we can come over here. We're going to do this. Camera is equal to new camera, this shader to pass in. And then we have our screen size, which I'm not going to worry about it right now. I'm going to say it's like 800 by 600 and just leave it at that. No other reason. And then finally, remember, anything that's closer than a value of 1 is going to not show up. So we need to actually move our camera backwards just a little bit immediately to be able to see our object. And then finally, we need to do this camera update to be able to update it. And now, if we go ahead and we run this, second to compile. Once it is finished compiling, we have our object being drawn right there. So it doesn't look too much different. So what we're going to do is we're going to now add in some basic first-person shooter code. This is the very, very basics. This is kind of the first big steps for it. But we're going to go ahead. I'm going to get rid of that, and we'll change that to something else in a second. But if we push the right key, this is important. Camera, translate. So if we push the right key, we want to move the entire scene to the left. Okay? And this is so important. And an easier way to do this, which we're actually going to do real quick, I didn't even think to do this, but this will make your life easier, is we want to go ahead and make each of these negative. The reason being that we are going to be translating in the direction opposite of where we're going. The same thing goes with our rotation. If we're rotating to the right, we really want it to be to the left. Same vice versa. So we go ahead and we do that. So what we want to do now is we want to translate it, and we don't want to translate a whole lot. We only want to translate a little bit. Otherwise, it's going to move really, really fast. So if we're moving to the right, we're going to say 0.1. And if we go over to our camera, that's actually going to be 0.1 to the left. It's actually going to be shifting our scene the opposite because it's going to be the camera moving in this case. Now we can go ahead and we can copy and paste this, and then we have our left key. I actually do left, right, up, down. I'm very picky about that. And this is going to just then translate negative. Oops, not that one. The left one will be negative. Now that we have that, we need to do up and down. So we do up, and we have down. And this is going to be very similar. It's just going to be our z-axis. Now the reason for that is that we're going to be going forward and backwards. So if we're going forwards, we're doing positive, and if we're doing backwards, we're doing negative. I believe correct? Correct? No, backwards. Forward is actually negative. Backwards is going to be positive. So we go ahead and we run this, and we go ahead and build this, you'll notice that we can now move backwards and forwards. Now, of course, the reason nothing showed up at the beginning is because our set translation, now we're moving back to, so that has to be positive as a result. So if we go ahead and we run this, we start backwards a little bit, and then we can push the down key to move back further, the up key to move forward, left to move left, right to move right. And that is our basic first-person shooter camera to kind of start things off. This is kind of our basic movement to start out with. Of course, you could change this to be WASD pretty easily. In this case, it would be A, right would become D, up would become W, and down would become S. Good. And now if we go ahead and we do this, we have WASD controlling for this. And that's kind of our basic tutorial for today. That's our very basic camera movement. To kind of kick things, to end things on another note, I'm going to go ahead and talk about a few things. So next week we'll be going over rotation. That's going to be a whole different ball game because we're also going to show how you can rotate with the mouse, which is, again, in and of itself a totally different thing. And so that's going to be next week's tutorial. Another thing I want to talk about today is Vulkan. So in case anybody keeps up with this, Vulkan came out last week, or this past week. And Vulkan is actually a pretty neat little thing. It's a nifty little new graphics API. And certainly not little by any means, but it is effectively a brand new graphics API. It is the successor, in effect, to OpenGL, and it is designed to be very low level and close to the metal. I am not going to be covering that on any of the coming up tutorials. I do not have enough knowledge of how to use it and such. I've only just started going through and getting this. Let me see if I can find the examples that I have lying around. So this is some code I found online that I've been slowly learning and figuring out how it works. In this case, let's go ahead and we'll set up to run this one. So I've been going through and slowly learning it. If we go ahead and we run this, you can see basically a little sample that they have for Vulkan so far. There's a whole bunch of them online. But I might spend some time in my free time going through and learning how all of this works, and designing some new stuff. And maybe I'll do some live streaming for it. But please don't expect too much from that. If I do end up live streaming it, it's going to be separate from this. It's not going to be anything professional. It's not going to be anything showing you guys how to do it. If you have questions, I can maybe answer some things. But Vulkan's a pretty nifty API. Maybe next year I'll do a tutorial on that. It's very, very cool, though. I'm excited for it. Big things that it brings to the table is it brings to the table multi-threaded rendering, so we can actually have multiple threads rendering objects. I think there's some really, really neat stuff that could go on with that, and I'm excited for it. But yeah, so this week expect me to stream some development as I go through and handle our rotations, figuring out our mouse movements, getting that set up for next week's tutorial. And if you're interested, again, feel free to tune in. That's just going to be me going through and getting things ready. But that's really it for today's tutorial. I hope you guys have enjoyed this. I hope you guys are finding these video series a little bit better now. I apologize again, the beginning was a little rough. Now it's getting a little bit smoother, so we can go through and very quickly go through and get some of our basic stuff going on. So right now we have our basic square. We've got some basic controls. Next week we'll get into rotation for mouse movement. And then after that, my plan is to go into texturing and showing how we can get this quad to actually have some textures to it. And then hopefully by that point we'll have enough very basic stuff to start doing a very, very simple, completely flat two-dimensional shooter, or three-dimensional shooter, and doing a basic game with it. So I know that these are kind of taking a while to actually get into making a game, and I apologize for that. I'm really trying to break these down and give them into bite-sized chunks rather than, hour-long videos, hours and hours like last year's. So please, if you're watching this on YouTube, leave feedback as you desire. If you're watching on Twitch, please leave feedback there as well. I always love hearing what you guys think. these videos. Again, I'm trying to make them more manageable. I hope that this is working out and that you guys feel like you're learning a lot and that you're not having to sit through hours and hours of videos. And I've had some questions regarding doing like a 2D Pong game with SDL. Maybe we'll go into that. I'm not opposed to that, but that would probably be after this. The goal of this is to focus on three-dimensional games for right now. Yeah, that's going to be it for today's video. Thank you guys for tuning in. I apologize for the delay again. Today's my birthday, so I am getting ready to celebrate that, and so I've been trying to set up for that. I just got registered for Comic-Con. I don't know if there's anybody that watched this that's going to be at Comic-Con, but if you're there and you feel like meeting up with me, just let me know. Send me a shout-out on Twitter or send me an email or something, and I'd be more than happy to meet up with you guys and talk with you guys, and, you know, I'm going to be there, so, yeah, thank you guys for tuning in. Hope you guys enjoyed it. See you guys next weekend.